Okay, let's go ahead and get started here. Pleasure to be here again, speaking to everyone, and thanks for attending this session. I just want to get some kind of gauge of experience in the room. If you've been in the battery industry for more than 20 years, please raise your hand. Yeah. Okay, only two people. If you've been in the industry, the energy industry, not battery or renewable, just generally the energy industry for more than 10 years, raise your hand. Okay, a few more. If you've been in the industry for 5 to 10 years, raise your hand. You've known a lot for 5 to 10. Less than 5. Okay, few people. One more question. How many of you in the room owns an EV, electrical vehicle? Okay, 1, 2, 3. Perfect. So maybe that's not. I was going to relate to EVs quite a bit in my presentation, so maybe that's not the best way. I'm assuming everyone has a cell phone. Yes. Okay. Perfect. We'll use that then. No pagers. Yeah. Absolutely not. Cool. The way I would like to run this session to be is more interactive. I would like to get questions as we go. So we have 5 main topics that we're going to run. So I'm going to actually break after each topic and ask for questions. I think this is going to be the easiest to digest for you guys and also the more effective to have a conversation. This is intended to be super high level. This is kind of battery 101. There are a lot of topics that we could cover, and you'll notice as we go through the presentation, there's a lot to be talked about. We can have follow-up sessions. Feel free to reach out to me afterward or after the session as you like. So we're going to talk about the best fundamentals, and I covered some of this in my presentation yesterday, if you've been to that, but we'll retouch base on it at the beginning. Then we'll dive into the best integration. What does it take to put a battery project together? Then we'll talk about applications. There's so many applications for battery storage. So far being utilized about 13 different revenue streams to use for a battery. We'll talk about the operation and maintenance for batteries, what it takes to really run these systems after they're built. And the last topic, which is the levelized cost of storage, LCOS. I'll present that as what is the industry considering the metric for LCOS, but in my view, it's still under development. There's a lot of questions that are still open, even in an industry level. So with that, let's jump to the technology and fundamentals. So sure, some of you, or if not most of you, have seen this picture from yesterday's presentation. There's multiple or 3 forms of storing energy. But let's talk about the fundamentals. Why do we need to store energy? Energy is a commodity, and it's one of the few commodities that don't have established storage mediums, right? So oil and gas, for example, you have gas tanks to store gas, right? Food industry, you have fridges and distribution centers where you can store that food. When it comes to energy, there is not a lot of established ways to store it to use it later and be effective. So it's kind of the fundamentals has been energy shifting. Let's store things that we don't need right now and use it later when we need it, and it helps kind of utilize the energy better. In terms of forms, there's mechanical forms. We talked about pumped hydro, which I find super interesting in the context of Oman. We talked also quite a bit about the chemical energy, which is the batteries. And this is really the technology that we're going to spend most of this presentation talking about. But there's also thermal energy. A lot of new technologies out there. They're trying to tackle the energy storage issue with some form of thermal energy storage. So let's jump to some of the key concepts. And this is what we look at when we evaluate different technologies, different forms of technologies. Mechanical, kinetic energy, or mechanical, or electrochemical. So we look at these parameters and more. I'm just highlighting really the really key ones here. But even within the same technology family, we also look at these parameters to evaluate different suppliers and different technologies within the same family of technologies. So I'm going to go through one by one on these and share some thoughts. So starting with energy density. Energy density is how much energy you can fit in the measure in the industry is a liter, okay, which maybe does not relate to many of you. How do we measure, like, why do we need to care about a liter? We care about a square, a physical space, not a volume, right? So there's another measure about how many megawatt hours you can fit in a square meter as well. So there's two measures for that. The reason this is important is if you think about energy storage, it's better suited, generally it's better suited next to load centers or large loads. That's where you serve those loads and you get closer to them and realize efficiencies. Load centers, especially when we think in the context of North America, where industries have developed, a lot of these major loads are close to major cities and in very attractive locations. So to give you a measure on energy density, in California, for example, we have a huge energy storage rush where we're installing a lot of systems, and every square inch matters. California is a very difficult state to find land. It's very developed, very populated. So an acre in California to put an energy storage system in could cost you up to $10 million per acre. An acre, I believe, or I think 3 acres is one FedDan. I think that's kind of the measure. So it's a third of a FedDan. I don't use that measure, so I hope I got it right. So think about it. It's $30 million to have one FedDan, which is quite expensive. So that's why energy density is a very important metric commercially when you evaluate different systems. And that kind of goes hand in hand with power density. So power and energy are theoretically, when people think about it, they're coupled, but they could be decoupled as well. So I'll give you an example. 100 megawatt, that's power. When you say 4-hour system, that's 400 megawatt hours of energy. So the duration where you could discharge or charge that capacity could be different between maybe go for 1 hour, 2 hour, 4, 6, 8, whatever that is. But there's also a decoupled approach when you use different technologies. So for example, flow batteries, you could have a larger tank that represents more energy, but a smaller power system that represents the power. But both are very important. You want to have a power density and an energy density. Now, in the context of Oman, this might be a little bit more forgiving than the context of California. So that, just keep in mind, it's not every region, every grid has its own uniqueness and has to be considered. Then the next one is cycle life or throughput life or throughput energy. So what is a cycle life? A cycle is a sine wave. So if you start at 0, you go to 100, you go to minus 100, and you go back to 0. So that's a full cycle. And again, context of energy storage is you start at 0 megawatts, you go up to 100 megawatt hours, you go down to 0, you're going down to minus 100 megawatt hours, which is your discharge cycle, then you go up to 0. So that's kind of a full cycle. But cycle could be, you could partial cycle, meaning you could go up to 50 megawatt and then go down to maybe 0 and then go back up to 50. So there's different variations of it. So that's why we came up with a throughput measure. Throughput is, if you have a 100 megawatt hour battery, then your throughput energy, your cycle is 200 megawatt, which is 100 megawatt charge, 100 megawatt discharge, megawatt hour, sorry, discharge. So that's your throughput. So that's a very important metric when it comes to degradation, and we'll talk about it later in this presentation. So the more you cycle, the more your battery is going to degrade. The less you cycle, the better your battery will perform. And different technologies have different cycle lives. For example, pumped hydro has an infinite cycle life. There's no reason to believe, other than ongoing maintenance that you have to maintain your system, there's no reason to believe that your reservoir is going to be impacted. You have the reservoirs there, physically there. With batteries, electrochemical batteries, this is less forgiving. The more you cycle, the more stress you have on the battery. The next measure is round-trip efficiency. And what does that mean? So if you're starting at point A and you're trying to go to the point of interconnect, which is the grid, and taking it from the grid back to point A, which is your DC battery, how much of the energy that you charge you can get to discharge. There's losses, transformer losses, inverter losses, cable losses, battery efficiency losses. So that's the measure. Like, what is your full losses across from a full charge to discharge cycle? And different technologies have different losses. Electrochemical technologies like lithium ion is doing impressively well. On a DC level, you can get batteries that are up to 95% efficient. On a complete level, up to the POI, including basically your inverters and transformers, you can get up to 90%. So if you're charging 10 megawatt, you're discharging 9, which is pretty impressive compared to other technologies. If you look at thermal, for example, at most you can get 65%. So if you're charging 10, you're getting back 6.5. So it's not very efficient. Pumped hydro is slightly more efficient, maybe getting up to the 70, 75%, but still electrochemical energy is very impressive when it comes to RTE. Depth of discharge. So another interesting topic in the industry is how much can you get out of your battery? And the example I was going to use the EV, but sounds like that's not the best example. Let's use your battery. So if you're in your battery, you have the readings of 0 to 100%, right? So how much can you effectively use out of the 0 to 100%? Virtually with your phone battery is 100%, right? You can go all the way up to 100 and go all the way to 0, and then your phone dies. So that's 100%. With large-scale energy storage projects, you can go all the way to up to 100. You can go all the way down to 0. With electrochemical energy, with special lithium-ion batteries, what we've seen is you can go all the way up to 99% because there are massive amount of cells that all can be synced together to get uniform 100% across all cells. And we'll talk about this later in the presentation. Similar, when you go to discharge, you can't go all the way to 0 because some cells will go to 0, but not the entire system. So when you average the entire system, it's not going to go to 0. So with electrochemical, we've seen that being 99.1%, so you're only losing 2% in your depth of discharge, which is, again, great. Similar concepts can be done for thermal energy and pumped hydro, for example, where it's not like you can empty every single drop of water in your reservoir. There's going to be something left, right? So that's kind of what's considered the depth of discharge. The other concept is self-discharge rate. So maybe the easiest way to explain this, again, taking the phone, your cell phone analogy, go ahead and charge your phone to 50%. Leave it on a shelf for 5 days. Come back to it, it's most likely dead by then. That's your self-discharge. So how much your battery is losing without really effectively using the battery. So that's your lost energy. That's called self-discharge. Parasitic loads and aux loads. Many of you know that batteries heat up when they operate. When they charge and discharge, they produce a lot of heat. So most of the systems, utility scale systems, have cooling systems involved in them. Air-cooled, liquid-cooled, whatever that is, there are cooling systems involved. But there's also control systems involved, right? A lot of measuring, metering devices, control devices. There's a lot of other devices, we'll talk about them later as well. So all of these consume power. So how much of that power consumed, what is that power consumed is the measure of how much auxiliary loads you have. So these varies per system, varies per technology. So the less aux loads you have, the less electricity bill you have to pay to run your system. So the less aux, the better generally is. So the next one is state of charge management. Another very interesting topic in the industry, and especially gets more complicated in electrochemical batteries than, let's call it, traditional batteries. So what is state of charge? So how when you look, and we'll take the phone analogy again. So when you look at you put your phone on charger, you see that percentage of the battery life going, or the battery charge going up, starting like 1% at a time and keeps growing. How accurate is that is really the question. So with LFP batteries, the way it's represented in the phone charging example, it's linear. So the more time you have your phone on charge, the more it's increasing its charge. But if you take an EV battery, it's quite different. You plug in your battery, you see your state of charge increasing in the first 10 minutes quite fast, but then after that slows down significantly. So that's called correction of state of charge. So the battery, the way LFP works, or general electrochemical technologies work, they call it the knee-jerk curve. It's very linear. It's hard to differentiate the voltage because it's such a millivolt readings. And then all of a sudden, the battery finds itself, oh, I have so much voltage in my battery, I have to jump to correct my state of charge. So state of charge management becomes very critical when you work with multi-megawatt-hour systems, because as a system operator, you don't want to find about your state of charge or how much megawatt hours you have in your battery on the 11th hour. You want to have that planned because you want to know how to manage it in case you have to discontinue a charge cycle and jump to a discharge cycle. There are different methods. We can talk about it later as well, which is bleeding resistors, internal balancing methodology, and state of charge correction logic. So that's another important topic, and it's different for each technology. NMC is different than LFP. Pumped hydro and thermal energy is different than electrochemical. So each one has its own way of managing that. The other one is rest time, and we'll touch about this later in the presentation in more detail. But just to kind of, on a high level, is we'll take the EV example, maybe it's better. So to extend the life of your electrical vehicle battery, it's best not to charge it fully and run it at full speed right away, right? You want it to cool down. It's a temperature that you're trying to keep it down, hot spots, try to keep it down so battery structure doesn't get damaged. So theoretically, you have 0 seconds rest time needed for an electrochemical battery. It can operate, there's nothing stopping it, but it's not good for its longevity of operation. So ramp time is how fast the battery can go from 0 to 100 or 100 to 0 or anywhere between. So each battery have its own characteristic. For example, thermal energy, it's not that fast. It's anywhere between 10 to 15 minutes to ramp up. Pumped hydro is somewhere around that 10-minute time frame. When you talk about electrochemical energy, it's 2 milliseconds that you need, 2.5 milliseconds that you can go full from 0 to 100 and 100 to 0 from a power ramp-up standpoint. Uptime and availability is another important aspect, which is how many failure points you have in your design, and how much your system is effectively available to participate in the market. And that all depends on the design of the system and the cell design as well, and basically the ability to bypass internal failures within the cell. So having cells in, I'm not sure how familiar are you guys with the cell nomenclature is. There's what's called 1B 22.4CS. So that's how many cells in parallel and how many cells are in series. And it depends on, based on that structure, you could realize, okay, if I have more in parallel, then I can bypass failed cells. If I have all of them in series, then one cell fail, you're gone. So that structure is very important. The nice thing about electrochemical batteries, there have shown in the industry, the past 10, 12 years we've been running these in the US, that you can get up to 98% availability in your battery system, which is quite impressive. In Calpine, we operate a large fleet of gas-fired generation, a large fleet of batteries, and we're considered one of the most reliable, high availability generation companies in the industry. Our gas fleet barely hits 90% availability. Our battery fleet hit 99.2% availability, which is quite impressive. Another point that didn't show here for whatever reason, it's operation range in terms of weather conditions. So batteries typically operate between minus 20 Celsius to 50 Celsius without derating. But if you go above 50 Celsius, then you start experiencing derating, and same if you go below minus 20, you start experiencing derating. So it's not really the weak link in the chain of the battery design, it's actually the inverter. The inverter has a much narrower operation band when it comes to temperature. They typically start derating above 40 C. So batteries generally fine. It's really your inverter that's going to dictate the design. So let's talk about technology trends. And really this graph I found interesting, and maybe some of you guys in the industry, especially in the gas industry, will find this interesting. Lithium batteries, you see that in the green circle. This is showing your energy density and what's called specific energy, but let's just focus on the energy density for a minute. So your lithium battery is anywhere between 7 to 800 watt hour per liter. That's kind of the measure for lithium ion. This is practical. This is what we have in the industry. We're hitting closer to 900 these days. But you see gas. So the gas is around 9,000 watt hour per liter, which is quite impressive. It's very energy dense. But the problem with the gas is as soon as you turn that gas into electricity, you have a 33, anywhere between, let's call it 25 to 35% efficiency. So you lose a lot of that energy in conversion. So with lithium ion, you have that 800, let's call it 800 watt hour. And we just stated that this is about 95% efficient. So whatever you have there, you're getting pretty much. But there are other technologies. This is not just lithium ion. There are other technologies like vanadium that was talked about a couple of days ago from some of the presenters, and flow batteries. So the problem with these, you see how the energy density kind of drops quite a bit. There are better lithium ion batteries as well that are in advanced R&D, lithium ion sulfate and sulfur and lithium ion air. Those are very interesting technologies. We expect those to be really game changers when it comes to electrical vehicles. And when you hear about in the next 5 years we might be hitting 1,000 kilometers EVs, that's really the technology that we're counting on pretty much. So the reason why I'm kind of converge on electrochemistry is really for some of these reasons. Energy density is very important for us, so that's why we consider electrochemical energies to be the energy of choice or the battery of choice, and RTE. So we see sodium ion is another interesting technology that is also breaking into the market. This is basically a cheaper alternative for lithium ion. Similar concept of operation, but instead of using lithium, you use sodium, and sodium is a lot more cheaper and more abundant to find, like compared to lithium. We've seen actually the first sodium ion battery go into operation this year in China. In a vehicle, in an EV. So they have a small car, I forgot the brand, but the battery is made by CATL, and they're testing that right now on the road. So that'll be a very interesting pilot to see how things go for it. But I want to really focus on the more dominant lithium technologies. I'm sure a lot of you heard about LFP, NMC, and NCA. And NCA, think about it as your very early Tesla Model S. If you have a Model S, and if you that's the battery that goes in it. It's the NCA. It's a very good technology from an energy density, and this measure really shows you how well it performs in each aspect or in each metric. So it's really good when it comes down to energy density. It's really bad when it comes to safety. It's a much less stable chemistry, and it has a tendency of catching fire. And we'll talk about fire and reasons of fire for batteries later in the presentation. So from NCA, we move to NMC. With NMC, it's a nickel, manganese, cobalt. Sorry, NCA is nickel, cobalt, aluminum, and NMC is nickel, manganese, cobalt. So cobalt is a problem, right? It's a very rare earth metal. It's mined in most of the time in Africa in really unethical mining practice. So industry has moved away from that quite a bit to avoid it, but also does not perform well when it comes to safety. A lot of the fires you'll hear about in the news, if you're following energy storage fires, I would say 99% of those fires are RMC or NCA batteries. They're much less stable batteries, but they present a lot of energy density improvement. LFP, on the other hand, this is becoming the dominant technology in the market as of today, has improved quite a bit in the energy capacity front. So this is an older graph. When I say older, maybe it's a year old, but this energy capacity has actually moved up. It's very safe. and it has a long cycle life, and it's a lot cheaper as well than those other technologies. So you see a lot of those LFP now hitting the road. Model 3, if you guys are familiar with the Tesla Model 3, the Tesla Model Y, those all are using LFP batteries. If you're familiar with also like the BYD vehicles, BYD is a Chinese supplier. Those are all LFP cells as well. So this is gaining a lot of attention. And I would say in the stationary storage, in the utility world, LFP is the #1 technology at this point. Most of the systems installed are using LFP. And when we talk about improvements on the systems, it's really material science. How better can you make your chemistry? How better you can make your components in that chemistry to have less resistance, better bonding, and better conductivity. So that's a lot of the work that's been done in the market. So let's look at this. So we talk about batteries, and what is a battery? And we'll talk about it in more details here. So a battery is simply an anode and a cathode and a separator sitting all kind of submerged in an electrolyte, which electrolyte, think about it as your conductive medium. Your separator is what prevents your anode and cathode of short-circuiting together, but it allows the electrons to flow in between. So cell design. So this is the theoretical of what a cell looks like. This is practically what it looks like. There are 3 more dominant cell design structures in the market. Each one of them has its advantages and disadvantages. Just to give you really high level, this is called cylindrical cell. It's more common in NMC batteries, and this is what you're going to see in your Model X, Model S, for example, as the Tesla's cars. If you look at this is called pouch. This one on the left. Pouch is an older technology that mainly used for NMC, and it's all about stacking sheets of cathode and anode and separator on top of each other. This is actually rolling those sheets together. This is a lot more dense. This is a lot less dense. This has an issue of expanding and contracting. So a pouch is basically a bag. It expand when you're charging it, and it contracts when you discharge it, which I've seen to cause a lot of cracking on these cells. This is a prismatic cell. It's a metal framing, and this is what you see a lot of the times in the LFP cells. This is kind of more LFP tailored, and really you take these rolls and you start bending them on top of each other. This is the most dense. This is the least dense. This is really a medium that kind of improves cell performance. Still dense, but also is not very costly. This is a very costly manufacturing process. So we take the cell, which is this. We start wrapping it into these batteries. So this is what's considering a battery. And then we start putting them in modules. So this is what a module looks like. Module has multiple cells, and on average, they're anywhere between 112 cells to up to 224, and even now we see more cells backed into a module. Then a module goes into a rack. So a rack, before jumping to that, so the module have a control system as well. It's called the battery management system, level 1 battery management system. So this is your level 1, and it gathers data from the different cells and reports it to the level 2 in the rack. And we'll talk more about the control systems in a little bit. So you get a lot of these put in a rack, and that's your rack, and that rack goes into we're calling an enclosure or a battery energy system. So you have multiple racks that look exactly the same, multiplied to get a higher energy in a container. So really high level, what an energy storage project look like. The battery enclosure, the DC block we call it. This is what was in the previous slide. This is this DC block, just batteries. And inverters, basically, to take that DC energy and convert it to AC. Well, the other way around, you take the AC energy and convert it back to DC. Then I'm assuming everything from here down is you guys are very familiar with. I don't have to really talk about it. It's very standard substation type design. On the control level, there are two new components that are added to energy storage system. So in a traditional substation, you have your SCADA, your metering, your power plant controller, and all that. So that's easy. On a battery, you have 3 levels of BMS. So BMS level 1 is on the module, BMS level 2 is on the rack, BMS level 3 is on the container. Then those BMSs talk to something called an energy management system. And the energy management system takes the data from the BMSs, takes the data from your cooling systems, for example, takes the data from your fire alarm systems, take the data from all the subsystems within the system, and does the intelligent processing of that. This is a kind of, let's call it a typical layout when you try to lay out the design for a battery system. So you have your roads, you have your equipment, you typically line up your batteries all together, your inverters come at the top or at the end of that lineup, and then you have all of your auxiliary systems. You have your distribution panels, your aux transformers, and your network all together, and basically that all ties together and ties to a substation somewhere here. So just want to kind of give you a view of what this looks like. It's pretty simple. That's what we like about it. The intelligence or the design and the technical challenge, we try to keep it off-site. We try to keep it in the factory where we have to integrate the systems and keep it pretty simple when it comes to site. I'll give you a view. This is actually my project. So it's called the Nova BESS. This is the world's largest energy storage facility in Riverside County, California. So this is about 3 gigawatt hour project that hit service 3 months ago, and it's backing up the LA basin in California. So this is actually an actual picture of the site. So maybe some of you thought it's a rendering. I think it looks beautiful and it's built well. So the reason we have some construction, this is actually going to be an expansion to this project where it's going to take it to 3.5 gigawatt hours by the end of next year. So just some interesting facts about this project. This used to be a gas plant, 750 megawatt gas plant. You're familiar with it. It's called the Inland Empire. That was a GE system, H-frame, if you guys are familiar with that. And that was taken out, and we pretty much installed batteries instead to respond to the market need in California. So these are the DC blocks, these white boxes here. This is the inverter right here. See that kind of similar to that drawing that we showed earlier. These are distribution panels for your aux system. These red boxes are your fire alarm systems. And they all tie together to a 500 kV substation and a tie yard, and this supports Southern California and the LA region. So just to give you an idea of development life cycle and how long it takes to build such a system, this idea came up in 2021, where we thought about, okay, our gas plant is not performing well in the market. The market needs a fast-acting resource. The gas plant takes it half an hour to ramp up, half an hour to ramp down. We're not capturing the revenues from the market. It's not doing its job. We need to do something else. So the idea started in 2021. It took us most of 2021 to really remove the system. So we had actual power plant in there. So we had to demolish all that stuff. So that was the bulk of 2021. And we broke ground on this project in September of 2023. And we got it done in June 24. So less than a year. And this is actually the largest battery storage project I mentioned in the world, but also this is about 15% of the 10% of the installed capacity in the US for 2023. So that's 10% of the market right here. So pretty impressive when it comes down to like how fast you can apply these systems. New build battery plants takes anywhere between 3 to 5 years. We're talking about less than a year to put a battery storage project in place. So with that, I'll stop here and I'll take questions. Any questions? Please go ahead. Do you have a mic? Go ahead. I can repeat the question to the group.
Regarding this picture, now we're talking the concept of battery, yeah?
Yep.
Yeah. Okay. Now, where do you get the charge, and what is the concept of using this one? I mean, use it for emergency, use it for night. using it night duration, or maybe you join it with the ecosystem,
Yep.
which is solar cells and so on.
Yep. So the question, the first question is how do you charge these batteries? This is the interconnection to the California grid. This is the 500 kV tie. So we charge it off the grid. So we charge it pretty much from like any load that is connected to the grid. So we charge it from there. There are a lot of solar farms in Riverside County. So we're not directly interconnected to a solar farm, but most likely the energy is coming from a solar farm because of that region right here. Your other question is, what is the application for this project? What is it used for? So we'll talk about more about applications later in the presentation, but just on a high level, this is mainly for energy shifting. There is a huge solar build out in California. Your noon hours, you have closer to about, I want to say 35 gigawatts of solar that kicks in. And the load does not need all of that. And so we have to reserve to storing that and then in the noon hours and use it in the afternoon peak. So a lot of this application is energy shifting and ancillary services as well. So we see the ramp up, the afternoon ramp up in California puts a lot of stress on the grid, where we see voltage and frequency being impacted significantly because of the generation drop and the load increase. So this kicks in pretty much in those hours, and you'll be surprised. This actually does a lot of VAR support. So we don't actually discharge the energy. We just run the inverters to absorb or contribute VARs as well in some instance. So those are the main two applications. But it's also designed to a black start application in the LA area. So if LA goes dark, if we lose the LA grid, this is actually one of the main facilities that it's going to regenerate or introduce or make up the grid or build the grid in the California, in the LA region. So those are the three main applications generally. This is a tradable asset, and I can spend a lot of hours talking about it, but I'm going to be very brief. Yeah, go ahead, sorry.
What is the cooling system involved here for the battery?
It's liquid cooling. So we have a closed loop cycle or like a glycol water mix that cools the batteries down. Yeah.
What is means how it participates in the grid control through like a dispatch control?
Yep. So
means how much megawatt it has to, means based on frequency or how it does? Yeah, thank you.
yeah, so I don't want to go a lot into that topic, but California has something called the CAISO, California Independent System Operator, the CAISO. The CAISO is the main operator of the entire energy market in California. So pretty much you get signals from CAISO to say, I need VARs, and you basically get that through a direct fiber signal to our controller, and our controller responds to that signal by ramping up, ramping down those systems. Energy is similar story. I guess I was going to mention about tradable assets. So this is a very tradable asset for us. The energy in California, or in some markets in the U.S., but let's just talk about California for a second, is traded on a 5-minute interval. So every 5 minutes, the price changes. It's like your stock market, right? You buy stocks, you sell them, buy low, sell high, kind of thing. This is exactly what we do with portion of the site, not all of it. Some portion of the site, we trade it on the market. So there's a day-ahead market, there's a real-time market, which is the 5-minute, and there's basically the contracts market and the hedge market. So we trade this on the portion of this, about 100 megawatt hour, we trade it on the real-time market, which we found is actually super interesting in California. This year or this summer alone, we had about 2 weeks of negative pricing where we get paid to charge the system. We literally get paid to use electricity. So you get paid to charge, and then you get paid to discharge. That's the perfect way to trade and make money, right? Like you just get paid twice to operate your system. So we found that to be a very interesting application. We see more and more, we call those merchant assets. We see more and more of these merchant assets coming in the US as well. So for the sake of time, we'll move to the next topic, but we'll take questions at the end as well. Best integration. So this is a look inside the box, right? So what is inside the box besides the battery? We've talked about the batteries. So we have a lot of safety systems, especially related to fire, and we'll talk about fires as part of this section as well, I believe. So we have a lot of sensors, gas, we have heat sensors, we have smoke sensors. Those sensors are tied to the fire alarm panel and fire alarm devices and controls, and that really, its job is to make sure that we don't catch fire. If there are any indication there is a fire, these systems will give us an early detection, so we stop the system from operation or intervene in other ways. We have, you see the BMS, we've talked about the BMS, you see the battery, you see the rack BMS in the bottom, and you see the level 3 BMS is for the entire container. A lot of cabling in between. We call these orange cables, we call them jumpers, which is very similar to the solar industry. You have jumpers between panels, and we have jumpers between batteries. Some systems have water connection, so you have a sprinkler system. Some of these systems have a sprinkler system. So if there is a fire, the best way to control a battery fire is to flood it, to put water on it and to stop the fire. So some of them require water systems, some of them don't, but this one comes with a system. The other fire mitigation method is called aerosols. Aerosol is a very common technology in the data centers. So this is like dealing with electrical fires. You put a gas, that gas extract the heat out of the system. But we'll talk more about that later as well. So yeah, I like to think it's very simple, and simple is good in power systems, because when you dispatch an operator to deal with this, you don't want him to be looking at 10,000 things. You want him to be looking at 3, 4, 5 things at that point. Cool. Okay. So control architecture, we talked about the BMS. So I know for the sake of time, I'm not going to spend a lot of time on this, but each of the BMS levels has its job. So the level 1 BMS really gets temperature, voltage, data from the system, and basically help the protection for that. Some systems do measure currents, amperage. It's very hard though to do that on a cell level, because these are very small readings. You know, they're in like a typical battery cell is about 3.5, 3.6 volts. So try to measure that on thousands of cells. It gets pretty complicated. Imagine doing it for an amperage reading. It's even more complicated. And then it goes up to aggregation on the rack level, then aggregation on the system level, or the DC block level, and then that's where your energy management system that ties all the battery controls to all the subsystem controls, and then this talks to your power plant controller, and this what talks to your control center. So if you have a control center somewhere, this is really what's getting reported to you by the energy management system. We talked quite a bit about fires, and these are becoming a very interesting topic in the industry. Recently in the US, we had a few large fires. Some of them resulted in deaths related to battery energy storage systems. Most of the fires, as I mentioned, are related to NMC batteries, and a lot of the incidents, the conclusion is people did not have the proper training. We have firefighters who show up to a battery system and they open the door. That's the worst thing you can do, to open a door on a battery system. So a lot of training is going in place, and we've been actually, as Calpine and myself included, we've been actually doing a roadshow across the US. We go to every state, every county, and we go and train the fire departments for a day or 2 days, typically, to know how to deal with them. But let's talk science. What causes a fire? Why these systems catch fire? So there are internal and external factors where fires happen on these systems. So the external factors is mechanical damage is a very common one. And this is actually very common in the electrical vehicle industry. There's a lot of standards on on testing for mechanical damage. The most famous one is the nail penetration test. If you guys have ever YouTubed that, it's really interesting. You see they literally drive a nail inside the battery and see how it catches fire. So there are also other shipment or kind of vibration testing, different kind of type of testing that goes into those systems. But the other reasons are related to electrical, which is overcharging, over voltage, and also under voltage, but also short circuit, external short circuit. The last one is heat, external heat. those systems are supposed to, cells can run up to like 60, 70 C. So they're very forgiving when it comes down to ambient conditions. It's best to keep them in the kind of 30 C range. That's what we'd like to keep them most of the time. That's why we introduce the cooling systems. But in some instance where, let's call it the subsystems failures or hotspots in some of your systems, bad thermal management design, you get some of these cells to go into higher temperatures, and that results in a thermal runaway. Similar factors are internal, so cell failures, bad QA/QC on the modules or on the cells, that results in short circuits, over voltage. But also there's really a phenomenon called dendrite formation. And this is basically related to the electrolyte. Electrolyte is a kind of a liquid kind of type or aqueous type medium, and we've seen with cycling, especially if the design and the testing is not, and the quality is not monitored, you have some hard formations in the electrolyte that acts as a conductor, like that short circuits the cell internally. So thermal runaway is what causes fire. Batteries and different chemistries burn differently. So LFP typically burns around 270 Celsius. That's kind of their burning rate. NMC burns are around 400 C, so they're much worse. So we'll talk more about mitigation in the next slide, but really there's the heat, and that the heat reacts with the electrolyte, and that causes your fire. So you have cell burning, then you have what's called propagation, and the industry is focusing on propagation. So it's okay to have a cell fail and catches fire, but it's really bad if you have a container fail and catches fire. So we try to keep it into failures happens, let's just keep it contained to one small component, not expand. So so the other subsystems that we have is deflagration. We talked about the incidents where some of the firefighters injured and some of them passed away. The more famous one is called APS, Arizona Public Service Utility, where that's what the deflagration design came out of as a learning from the incident, where we need to find a way. So when batteries, there's a thermal runaway and there's fire, there are gases, and most of these are hydrogen gases or hydrocarbon gases, and those need to find a way to be vented out, because you're creating a hydrogen bomb if you keep those hydrogen gases inside the container, and there's enough volume, and if you introduce oxygen to hydrogen, it burns and it explodes. So a lot of the designs are now around deflagration and how to get rid of those gases safely. There's a lot of innovative designs on how to do that, but we're not going to get into the details right now. So with each issue, there's the mitigation method for it, right? That's what we work on as engineers and as technology leaders, and finding ways. We live with the risks. Risks are there, and every part of our business involves a risk. It's how you mitigate it and how you manage it. That's really the key component. Again, for the sake of time, I'm not going to review each one of these in detail, but we pretty much found a solution or a mitigation plan for each of the failure modes, and this is part of the learnings in the industry. So those systems, the early systems that got installed, I would say 10, 12 years ago, didn't have some of these systems or these mitigation methods. But as we're learning, these systems are improving, and we have a much more developed standards and industry around us to develop standards and requirements for these systems. Okay. So talk about codes and standards. So I remember when I started working in energy storage systems about 12 years ago, we did not have a single standard for battery storage system. The only, I should say, the only standard we had is UL 1973, and that's coming from your cell phone testing requirement. That was pretty much the only standard out there. And since then, the industry has evolved to include a lot of standards. Some of them are international, like UL, IEC, IEEE, UN as well. So I would say a lot of them are international, but there are some local standards like NFPA. NFPA is the National Fire Protection Code. So Oman might have its own fire codes. I'm pretty sure they have no provisions for energy storage at this point. So it's part of the learning is to improve those codes and standards to make sure that the industry is trending toward a safe design and a safe implementation. And just to give you an idea, NFPA 855, I think, got introduced in 2015-ish. So years in when we start implementing systems. So we had systems that did not comply to any of these codes at this point. So, and these are being revised on a 2-year intervals most of the time, which is even not catching up with the industry. We see the designs changing almost every 18 months. So by the time you have your next code revision, that technology that you tried to address, it's gone, and you have to deal with something new. So we're trying to work with the NFPA and some of the standards agencies to actually have a much faster process to revise these codes. Cool. Not going to go into each one. There's a lot of codes. Some of you I noticed taking pictures. Feel free to research them, and if you have any questions, please let me know. Okay, I'll stop here and see if you guys have any questions. Okay. Oh, go ahead.
Regarding each enclosure, approximately how much it will, the weight?
Okay. So the question is about the weight of each enclosure. So let's go back to the enclosure and maybe explain a couple of things. So first of all, let me explain what is the size of the the enclosure. Like, these are typically 20-foot containers, literally the shipping containers you see in storage yards or shipping yards. There are some that are 40-foot containers, but mostly they're 20-foot containers. The industry is really evolving so fast. I remember my first container that I installed that was a 40-foot container had less than 600 kilowatt hours in it, in a 40-foot container. The system that we installed more recently, in a 20-foot containers, you have about 6 megawatt hours. It's a massive development. These are typically weight around 40 metric tons, so they're pretty heavy. And that's why we went from a 40 container to a 20-foot container, just from a weight restriction standpoint, to be able to ship them on ships and also on road shipments as well. Yeah, so they're typically around 40. Yeah, that's why they don't exist, because you don't have, in the US at least, you don't have ground transportation that can ship 80 tons on regular roads without a special permit. And special permits are pretty complicated to get. Yeah. No problem. Good.
What is dendrite formation and how to mitigate it?
I'm sorry. Can you?
Dendrite formation.
Yeah, dendrite formation is basically the electrolyte, as I mentioned, acts like a conductor that helps the flow of electrons, but the separator prevents the cathode and the anode material from contacting each other and shorting. So when the dendrite what happens is that electrolyte becomes solid. So it becomes like a wire. And that wire connects your anode and cathode together and short circuits the cell. So that's kind of the system. Yeah.
When we are talking of fire, basically there is generation of hydrogen gas inside.
Yep.
So is there any need of any specific equipments, like what we call it as hazardous equipments, like 2C type?
I'm sorry, what are these equipment?
Yeah, normally in oil sector, wherever we are having hydrogen gases, we use specific equipments which are suitable for 2C zone, means area classification, right?
Yeah.
Means flame-proof equipments or increased safety. So is there any need of using any equipments near these installations? Means, are we following any hazardous area classification or?
Yeah, so I'm not super familiar with those equipment. I don't know, are these mitigation equipment or help reduces those gases?
It is basically when we define that what is the probability of the generation of gases and how it can affect the environment or how it can be converted into a fire to avoid that.
Yeah.
So we are having a different class of equipments.
Yeah.
Because in refineries and all, where we are putting the battery storage for our emergency system, we define all the ventilation fans and everything based on these.
Yeah. Yeah. It's a classification of the risk.
Classification of the enclosure of the fan or any
Understood.
electrical equipment. So is there any classification for BESS it is required or not required?
Yeah, so that's a good question. So that's a classification question, not really a device question. So just to speak on devices, we do have hydrogen sensors. So we do have measurements. The industry and the codes has improved to require a mitigation method that includes ventilation, for example. Original project did not have that. So we did improve to actually include mitigation method like ventilation. There are other methods like sparking, they call it. So you burn the gas before it becomes too large volume that could actually cause a fire. So you're actually having small fires that are not going to impact the system. So there are different methods, but from a battery standpoint, we actually classify them as, I believe they're class 1 in the US, which means they're low risk, because as individual containers don't contain enough hydrogen to exceed limits to go to like class 2, class 3. So they're still individually looked at from a design standpoint. Yeah. Please go ahead. You have the mic, please, in the back. 3 rows down. Yeah.
Sultan from Sahara Aluminium. Just I have a couple of questions, in fact, related to this Nova BESS. I don't know if you have mentioned the capacity of the plant, which maybe I just missed it.
Yeah, 3 gigawatt hours.
3 gigawatt hours.
Yeah.
And I mean, considering the commissioning date, which you've mentioned, June 24, so that's a relatively new project.
Yeah.
So I don't know how is the Calpine experience and knowledge on this BESS isn't relatively new to the system, or you have a different experience on this. Secondly, what's the challenges? I believe there's some disadvantage of this system. I mean, it's worldwide, but you haven't mentioned about it, like the lifespan of the projects, the efficiency, degradation of the batteries, also the initial cost of such a project when you compare it to conventional power plants. So this kind of disadvantages, which maybe is good to elaborate a little bit more on it, so we can consider this. And lastly, what's the OEM of your batteries that you have been using this project?
A lot of questions. So first question is the challenge or our experience in the space. So personally, I've been doing this for about 12 years on battery storage specific in different companies, different regions. Calpine has only been doing battery storage since 2021. So that's the time when I joined Calpine, kind of really to start the renewable business. So that part of basically my strategy and my vision to integrate more renewables in the company was to go through solar and storage build out. So Calpine as a company, we don't have a lot of storage, but the team that works under me has the most experience in the industry at this point when it comes down to battery storage. Your second question was that disadvantages. Like any system, there's no perfect system out there. There are advantages, disadvantages. Some of the, I guess, disadvantages that we see with battery systems is the integration piece being a little bit more complicated because you work with inverter-based systems that require extensive controls. And that's been a lot of challenge in the industry about perfecting the inverter system controls. And in terms of cost, it's not expensive. I know there's this mindset in the market, thank you, that battery systems are expensive. They used to be expensive. Just to give you data points, my first installation 12 years ago, we were buying batteries for about $1,000 per kilowatt hour. That's very expensive. The most recent systems we've bought are closer to $100 per kilowatt hour. So quite a change, and we see the industry even improving year over year on that. I can't give you specific numbers on the project, too much to share, and I'm not here to market any suppliers. There's a lot of suppliers out there that can provide systems.
So what's the expected lifetime of this project, for example?
Design life is 25 years. Operation life that Calpine is planning is 20 years, but we'll keep evaluating as we go. And we'll talk about degradation in a later slides. We're touching on that.
OEM of these batteries?
Not here to do any marketing for any OEMs.
Thanks.
Yeah.
Thank you very much.
Yeah. Okay, let's move on for the sake of time. Yeah, best applications. We talked yesterday about some of 4 applications that I think observing the Oman market that could work, which is energy shifting, ancillary services, resiliency, and seasonal storage. But storage can be used in different places, and this is kind of the beauty of batteries. The same battery could be used in different applications, generate different revenue streams. We call that stacking of revenues. So we're trying to make as much money out of the battery, using it in different applications as much as possible. So I think I mentioned yesterday, the battery systems are becoming the operator's best friend. They love them. I remember my first battery installation 12 years ago. We're trying to convince the operators to use these things, and they was like, "No, we're not dealing with new systems. We have enough new stuff that we don't want to deal with it." We ended up installing the system and gave them a 2-year operation pilot just to kind of really learn it. And within those 2 years, we had the same operator come back and ask for more. I was like, "This is exactly what we need." They can act as a load. They can act as a generator. They're fast ramping, fast ramp down. They do a lot of really interesting and cool things, and they're easy to maintain. And we'll talk about maintenance later in the presentation. So not going to go through these one by one, but really generally there's called customer service services, which is basically somewhat behind the meter, individual use. You guys talked about solar, rooftop solar, and storage and all that stuff, so it kind of plays in that space. There's RTO or ISO services. This is kind of really the more common on utility scale. This is where the big utilities try to use these systems. And also the utility services, which is deferral of upgrades and investments. Because if you have a congestion in one area, but that's only seasonal, or that's only kind of time of use congestion, then you use those batteries to relieve the system, so you don't have to build and upgrade these systems. And this is a really very interesting application, and this is kind of really got the opportunity to build some of these systems. The first project in New York City that was in 2015-ish, 2016, that was really driven by distribution deferral. New York City is a very complex city. There's no way to build a new transmission lines. Or distribution lines is very complicated. So we worked with Con Edison to really strategically install different battery blocks across the city to relieve the congestion. And that worked really well. Since then, it worked so well that Con Edison decided to start a battery business themselves at that point. So the goal, the reason I'm showing this on the screen is to really encourage you guys to think about all the possible applications for batteries on the system. Don't just use it for one thing because you're not extracting the most value out of it. Use it for multiple things to try to make the return on your investment faster, and also fully utilize your battery system that you're installing. A very interesting topic in the industry, and we chatted yesterday with some of the folks in the room about BESS Plus, which means batteries can go with everything, literally everything. I've personally installed batteries with solar. I've installed them with gas plants, and some of you might think, I was like, why gas plants? Like, what can they do there? We've seen a lot of optimization on the gas operation profile using batteries. So for example, I'm sure some of you guys know this better than I. When you come to operating a gas plant, there is start count. So you have your maintenance cycle driven by how many starts you have and how many run hours you have. And once you start the gas plant, it has to run for a minimum hours, right? So it depends on the market, where maybe the gas plants don't have to run for a long period of time, or maybe they have to act as a fast response and they don't run as fast as they need to. Or as a black start service, if the grid goes down and you need to start your generation, then how do you use that? I think most of the time you guys are using diesel generators to black start your systems. We've noticed that BESS plus gas is becoming a very popular installation in North America and Europe. We've done BESS plus geothermal at Calpine. So we have a really large geothermal plant, and to have better firm capacity deliverability on that plant, we decided to put more batteries, and that helps us reshape and firm shape our generation profile. We've done BESS plus wind. I don't have it here, but we did BESS plus hydro. We had hydro dams that are also installed BESS for the similar reasons that I mentioned earlier. An area that we're very interested in right now, we don't have any installations yet, is BESS plus hydrogen. Hydrogen needs really clean power when it comes to power factor and power quality, and also could tolerate some power variance, but to get the best out of the hydrogen system, you want to have it as much of a fixed shape as possible. So we've seen BESS playing a role to really help out with, especially green hydrogen. If you have solar with hydrogen, so you put batteries, you firm up your capacity. So we've seen that. We've seen interest, but we haven't seen installations with that. This talks about DC coupled versus AC coupled systems. I don't want to go through that in details, but these systems could be integrated at different areas in your co-location site. They could be physically just sitting next to each other, but electrically not connected. They could be AC connected, sharing the same MV bus, or they could be DC connected, sharing the same DC bus. Each one has its advantages, disadvantages. It's a really big topic in the industry that it can't be covered in a few minutes. Long duration is gaining a lot of attention. We have been evaluating different technologies that related to long duration, and we see that market developing as a need in North America, given the higher renewable integration. You guys have heard about the duck curve, California duck curve. That's actually turning into a canyon curve, meaning you have two sharp edges, one in the morning, one in the afternoon, with so much renewable generation in between that now the 4-hour systems don't do enough to serve that market. We're looking at 8, 10 hours, but we're also looking at multi-day or intraday and weekly storage, up to monthly. A lot of systems out there that we're studying, we're piloting some of these systems in our grid. Some of you have heard, I've talked to, they're piloting some of those systems here in Oman as well and other regions. So very interesting to hear how that goes in the market in the future. Okay, stop here. Any questions on revenues and how to generate money out of these systems? Yeah, go ahead.
Hi, yes. You talked about the usage of BESS for relieving the congestion in the transmission.
Mm-hmm.
And you mentioned that it was positioned at the strategic spots. So just I don't know if it's a stupid question, but how do you know where? Is it like near to the generation, or it's based on data released by the TSO? And is there a need for it to be mobile? What do you think?
Mm-hmm. Yeah, very good questions. Thank you. So they're actually closer to the loads, not closer to the generation most of the time. Mm-hmm. We like those systems to be closer to the load. In terms of how we define the locations, we do a full distribution load flow studies, and we have dynamic models that we show. And I've heard some of you guys are doing that in your grid as well. I don't think this is exclusive to North America per se, but where we start virtually putting these systems and virtually operating them before they're physically installed, and see how that improves the grid. So it's a very iterative process. It's not just you pick a location, you do it. You actually do a lot of studies, and then you come up with those key spots or key locations, and then you start implementing that. Your second question was, I'm sorry. Need for it, yes. That's a very interesting topic in the industry right now. So there is what we call them storage in wheels. So literally your pickup, like your long haul trucks that have batteries on them and get dropped off at locations. Those are not considered utility applications at this point, because utility mentality. They like things to be long-term, fixed in one location. But we've seen that a lot in special occasions, special events, where you have these large events, large loads that are only for the short period of time. We've seen those systems being introduced. We've seen those systems actually being plugged to substations as well to improve the reliability of substations on shorter period of times. But it's not growing to be, I would say, a large industry yet, but it's definitely an application that can be used. Yeah. Any other questions? Yeah, please.
Yeah, regarding including BESS with another generation source, as you mentioned in the slide, what is the benefit as compared with having the batteries anywhere else in the system? Is it to minimize the losses, or is there something else
Yeah,
to consider?
yeah, there are few reasons. Depends on which application you're talking about. I think I went in length on the gas, why we're doing it with gas, just ramp up time and run hours, start counts and all that stuff. With solar, for example, we like it for capturing clipped energy. So clipped energy is a very common issue in solar where, for example, if you need 100 megawatt solar delivered, you build 130 megawatt DC solar. You have solar overbuild. For most of your day, that solar overbuild is being clipped, pretty much going to no use. So instead of clipping the energy, you charge your batteries if you have a DC integrated system. So you use that clipped energy to free charge your batteries for later use. So that's kind of maybe one of the reasons we use that in solar. For example, you save in solar, you save on equipment. You don't have to buy two inverters. You have an inverter anyways for your solar system, so you just tap to it, and with some intelligent controls, you can make it work. But yeah, wind is also to solve the issue with energy shifting and intermitting generation. Geothermal, I think I talked about firming the generation and improving the ancillary services there as well. So we see a lot of those kind of applications. Your other question is it better to be closer to the generation site or to the load? Our experience and my view is we like those battery systems to be closer to the load in general, but they also serve a good function closer to the generation in some occasions like these. So. I saw a question in the back just behind you, please. Yeah. And that will be the last question before we move to the next topic.
Yes, this is Moyed Al Muhammad from Oman's Hydrogen Center. I want to go back to the Nova site at California. I have a simple question. When you were converting the site from a gas plant to a battery energy storage system, did you face any challenges when it comes to like state law or government law? Even like during operation, are there like certain laws that you need to abide with?
You said laws and policies, right?
Yeah.
Yeah. Not really, because California, we talked about it yesterday, they're the greenies, right? Like they want anything that could possibly replace gas or fossil fuel generation. So when we came up with the idea, and remember sitting with the CEC and presenting that thought, they were very excited about it. They even, we're supposed to actually, the gas plant was supposed to be there for another 5 or 10 more years. So we proposed an early termination of the contract. We were supposed to pay a penalty. They waived it. They was like, okay, get rid of it. We're not going to pay. Don't worry about the penalty. Just get rid of it as soon as possible. So no, we didn't have issues from a policy standpoint. But that's different per region. California just being the policy, driving green policy. That was very, very interesting. But we've had a lot of challenges permitting the system from a ministerial permitting, like getting a fire permit or fire approvals, getting building permits, because now some of that site utilizes existing structures. We use the cooling tower foundation as a foundation instead of building new foundations. We use some of the tray systems that was already built for the gas plant to actually use for the battery. So we had a lot of that kind of brownfield type construction that required a lot of permitting. And that took some time, but I wouldn't say it was challenging. Yeah.
Thank you.
No problem. Okay, let's move to the next topic, and we'll open questions at the end. Yeah, so there was a question earlier about augmentation and overbuild and degradation and all that. So oh, sorry, let's talk about that. So yeah, batteries degrade. That's common knowledge. Everyone knows about that. Your degradation curve looks at anywhere between, let's call it 30% to 35% over 20 years. That's kind of the typical degradation curve on an LFP cell. But there are a few methods to make up for that. So practically there are three that we've seen and we've done, but there are more. This could come in any size or shape, as you will. So the first method is called overbuilding plan. So meaning if you need 100 megawatt for 20 years, then go and install 150 megawatts and let it degrade, and you'll be fine at the end of the 20 years. It's not very optimal from a financial standpoint. Understandably, you're spending more money up front, and technology is improving. Price is declining, so why buy expensive technology in day one? But we've seen other projects that is needed. For example, challenging locations for construction. You don't want to be back there every time because it's so challenging to build, right? You just want to do it all at once and be done with it. The other one is periodic augmentation, which is you build your initial system and you go in every year or two or a couple years and try to kind of build your system. And this graph shows you this is the initial capacity. The blue is initial capacity. So you see the initial capacity degrading. The orange is what you add as augmentation. Okay. And then we've seen a hybrid model where you overbuild for initial few years and then you go through a much lower augmentation cycles with overbuilding augmentation quite a bit. So as I said, it comes in all shapes and sizes here. So, but fundamentally, I guess maybe some of you think about, okay, why is it degrading in the first place? Why are these batteries losing energy and losing capacity? So, not to dive a lot deeper in this topic, but there is two degradation reasons. One is called calendar degradation. One is called chemical degradation, pretty much, cycle degradation. Calendar degradation is easy. Take your cell phone as an example. The day you buy it, it performs really well. It runs for 10 plus hours. 2 years in, it barely runs for 2 hours, right? It just, even if you don't use it, even if you literally don't use it, just sit it there. That's called calendar degradation. The reason is you have crystallization of ions and materials. So basically you don't use it, it starts crystallizing, it's really hard to extract it as a process. The other one is cycling. So the more you run the system, you can imagine you have two anode and cathode and something in between. You run something in between that separator. Some of those ions are some of those lithium ions that are passing, they're going to get stuck at the separator. They're going to bond with the separator. They're going to you're not going to have it for the next cycle. So you have kind of bonding with the separator as a major method, as a major reason for cycling degradation. So yeah, so those are some of the reasons why we have degradation in the first place. And we talked about cycles. The more you cycle, the more you degrade. So if you look at this graph here, you see if you run it for only 100 cycles per year, you're looking at the green curve, which is a lot better. Your system is actually not losing a lot of its capacity. It's maintaining almost 90% or above capacity in 20 years. You go and cycle it for 365 cycles, and you see that red curve in the middle. It's getting worse from a degradation point. Same for 500 cycles, and this goes more, like if you cycle more, cycle less, you can come up with different graphs. So other operating restrictions, we kind of touched on some of that, is resting time and resting SOC. So we talked about resting time. Not going to touch on that, but let's talk about resting SOC for a minute. So. Resting SOC is when you charge your battery, and EVs is a great example. So when you charge your battery in an EV, it's better not to charge it to 100% and leave it for a few days on 100% charge, because that's, think about it, when you put energy in a cell, you're adding stress to the structure. So you want to relieve that stress as fast as possible. You don't want to be stressed at 100% for a long period of time. So typical resting SOC we like to see is anywhere between 50 to 60% as a resting SOC. Resting SOC we like to see it in the 80% on the high end and the 20% on the low end. That's kind of where we like it to sit. On an average annual SOC is throughout the year, through cycling the system, we like it to be cycled. We don't like it to be underutilized. And if it's underutilized, you should keep it at a lower resting SOC. And that's the 60% I was mentioning earlier. So if you take an average, if you take all the data, hourly data for the cell over a year and average it, we like that to be in the 50 to 60% generally. And we talked about environmental conditions as well. So maintenance, so that's operation, this is maintenance. These systems require maintenance, but they're not extensive when it comes to maintenance. Especially your batteries and inverters require a lot of maintenance, or sorry, not a lot of maintenance, your periodic maintenance. So typically, a lot of the maintenance on the inverters are related to mechanical parts. There are a lot of switching devices, and those tend to break and have issues. So that's on the inverter. The IGBTs as well, and the electronic boards that we've seen that are overheating for different reasons. We're not going to get to it. This is a common issue in the industry, especially in solar, but it's also hitting the storage world as well. So a lot of those are inspection based, really, than fixing stuff. So you have to go there and look at it and make sure that you're trending. And when I say go there, you don't really physically need to go there. I mean, those are reported remotely. You can do analysis from your office and make sure that the trend is not getting worse over time. With the battery systems, it's very similar. It's really inspection based. It's a lot of it is kind of you don't have to go and change batteries. We don't typically change batteries. We put them and we leave them for 20 plus years. A lot of the inspections related to your HVAC equipment, like any HVAC equipment in your house and in other systems that you deal with, those tend to require a lot of maintenance. So that's kind of really a lot of the maintenance is related to HVAC, fire alarm testing, and each battery container, we haven't talked about it, but each battery container have its own UPS system. And this is not a requirement in different regions, but this is specifically to the North American market. The fire departments still don't accept that we have a battery that actually can back up those fire alarm devices. They're just still stuck in the old mindset that each fire alarm device have its own battery, even though it's within a battery. So we have to install these batteries pretty much, and those require some, and those are the what are they called? The substation type batteries, those that you have to replace every 5-6 years, whatever that replacement period is. So yeah, like this is literally all the predictive maintenance, I guess, or proactive maintenance that you have to do. Other than that, is really a lot of reactive. Like if there's a failure, you go and fix it. But those systems, I said, they have a pretty high availability. We haven't seen them fail that much over the past years. So with that, before jumping to the last topic, I'll take questions, and I know we're running out of time, so we'll try to keep it short here. Please go ahead. Microphone over there.
About the recycling of BSS. So you haven't talked about the recycling regulations and the impact of investment of BSS in the recycling in your evaluation of these different types of batteries.
Yeah, no, absolutely. That's a great question, and it's definitely a question that is being addressed in the industry as we speak. Batteries are highly recyclable. Recent studies, and we had one project that went through a recycling or an end-of-life recycling exercise. We've figured that they're actually 97% recyclable. So all the materials, other than plastic, which could be recycled, I guess, but all the materials that goes into the battery cell itself is recyclable. So we take the cathode, we take the anode, we take the separator through a chemical processes. We extract all the material that went in it, the lithium, the lithium, the nickel, like all these other stuff, and we can reuse it. There's no reason we can't. So it's highly recyclable systems. There are companies that are building up the recycling capability. The one that comes to mind is actually a friend of mine. We went to school together. He started that business, and it's called Alaydi, and they're present in Europe, North America, and also starting up in Asia. So yeah, they take those batteries, and what we strongly believe in this market right now is at the end of life, we expect to generate revenues by giving those batteries back for recycling. So that material is still valuable. So you give it back, discount the recycling cost, you're actually still making money back as a repayment for recycling your batteries. So this is still developing. As I said, we've seen some project goes through it. It's also driven by not really the utility industry. It's driven by EVs and consumer goods. Like all of your batteries in your cell phones and your laptops are being recycled as we speak. I mean, those are been recycled for years. But EVs is also becoming a big question about how much of your battery can you recycle, and that's being addressed as well. So, yeah.
First question is regarding the augmentation. What is the normal philosophy of augmentation?
Mm-hmm.
How is at what level the augmentation is done? Means module level or
Yep.
rack level, or whether we need to add any inverter also along with that. So what is the philosophy for augmentation?
Yeah, sure. So philosophy for augmentation, similar approach. There's so many ways of doing it. We've done it different ways in the past 12 years. We started with physical battery replacement. That was a bad idea. So take a battery out and put a new battery module in the same container. That was not the most optimal approach. We've seen DC augmentation, meaning adding more batteries on the DC bus, so sharing the DC bus. We've seen AC augmentation, adding it on the AC side. We've seen inverter-based augmentation. We've seen co-location augmentation. There's different ways, a lot of advantages, disadvantages for each topic. Not going to get to it, but really there's no wrong answer. It depends on specific on the project.
Second question is there any criteria while evaluating the batteries for the percentage of recycling? Means is there any, as a parameter, it is being defined for any battery system?
Yeah. So it's being defined. We've used it as Calpine, as my team. We've used that as a criteria for selecting suppliers and selecting technologies. I won't say that's a common industry-wide, but we do look at it. It's becoming, as I said, a very hot topic now. Policymakers or AHJs, or basically permitting agencies, are requiring a recycling plan as part of the approval process for a new battery system. So it's a topic that's definitely gaining a lot more attention, rightfully getting more attention. Okay, I'm going to jump to the next topic, last topic. Levelized cost of storage. So starting with the levelized cost of energy, it's really a simple concept. And as I said, this is nothing new. Honestly, this is an industry standard that's being used all over. The reason I put this on the screen and I want to talk about it is challenging the approach and have you think about how you should really evaluate the levelized cost of storage for a battery system. So LCE is pretty much how much energy produced divided by, the cost divided by the energy produced. That's as simple as that, with a net present value, and that kind of helps you evaluate different technology, different projects. The levelized cost of storage gets a little bit more complicated, where you have, which is really not, but let's just say it's still your cost of installation, your cost of operation, but then you start adding quite a few things. Now you don't have energy delivered, right? You're not generating new energy. You have energy charge, energy discharge. So you start measuring it by how many cycles you expect the system to run. So when you start evaluating a project, is this a system that's going to be running every day, or is this a system that's going to be running once a month? That's kind of really the measure that you start looking at. And what is the capacity factor of that system? And then you factor in the RT and depth of discharge. ITC is the investment credits in the US, so that's might be not applicable in this region, but that's there. The reason I brought this up, and I said earlier that I want to challenge that, is battery storage, as we spoke about it earlier, it has so many revenue streams. Some of them does not include discharging or charging energy. And that's not being credited, right? That's not being evaluated. That's not being something that's measured to say, yes, we add additional values. So that's kind of really the discussion in the industry right now, is how do we add more parameters to the levelized cost of storage to better value the value of these battery systems. An example I gave is MVARs, right? So you're contributing to grid stability, but this equation doesn't count for it. So even though you're giving services, you're not getting really the benefit of those services. We talked about deferral of investment. That's not being factored in here as well. We talked also about emergency and resiliency, and there's no measure for that in here, right? So all of these concepts are as actively discussed and hopefully we come up with an equation that is more inclusive for all the services and the benefit that battery storage presents, which will give storage better value overall. If you see that number, if this number goes down, then that's a better investment, right? So we try to bring this number down by including more benefits in the equation. So that's all. So I'll stop here. I know we have maybe 5-6 minutes for questions. So yeah, go ahead. Sorry, I'm going to go back to the Nova picture. I love it. I just like seeing it.
Thank you, Emad. It's really a wonderful, eye-opening presentation, I can say. So I have a set of questions, probably from first slide to last slide. So I just want to ask you one by one.
Yeah.
So can you just
Can we do one by one so I don't forget all the
one,
questions?
yes. Can you just show some, throw some light on the time required for engineering, permits, and procurement activities?
Yeah. So really it's hard to pinpoint a time frame. It depends on the region, depends on approvals, what agencies are involved in each region, and what systems are you using, right? If you're using lithium-ion batteries, for example, where most of the design happens way ahead of time, those are products, right? Those are not engineered system for an application. Those are products that you're buying. Then that cuts down significantly in your engineering time because now you're buying an engineered product already. You're not trying to engineer from scratch. Early days of storage, we literally had to engineer every project because there was no products. So we had to build products. Where now we have those products available. So that cuts down significantly. And in terms of permitting, as I said, depends on the agencies. We've seen permitting in Texas takes 2 months. We've seen permitting in New York take 3 years. So it depends on the region. Yeah.
And on the lead time, procurement timelines for especially on the batteries?
Yeah. This is very dynamic. It's driven by market, supply, demand balance, right? So COVID time, 2 or 3 years ago, we've seen battery lead times hit 2 years. And that was a problem. Recently, we've seen battery lead times around 4 to 5 months. So it depends on where we are in the supply demand from a market standpoint, but also depends on the raw material production, right? 2 years ago, we had a huge shortage in lithium that really had a huge impact on the industry as a whole. Pricing were record high, delays in delivering and all that. We've seen that pricing come down quite significantly the past year and a half, so that's improved quite a bit.
Yeah, so we understand presently market is evolving and capex is coming down drastically. So can you just show some, throw some light on capex cost over the lifetime?
Capex cost or OpEx, sorry.
OpEx.
OpEx, yeah. Again, really depends on the region, and OpEx is driven by labor cost because that's the labor that you have to do, right? In the region. California is very expensive. OpEx, electrician makes, I don't know, $60, $70, $90 an hour. Those guys are really expensive. Where in areas like Texas, we've seen that cost being significantly low. So it's really driven by region, similar to CapEx. I mean, other than your equipment cost, all of it is site construction and site hours, and that's driven by region and market and labor rates in each market.
Yeah, because we, as you said, we need to plan multiple augmentation in the project lifetime. So will that make sense considering BESS integration with solar and other generation mode?
Your question is about augmentation cost.
Yeah.
Yeah. So as I said, like it's really driven by market. So if your labor is not as expensive as California here, then maybe you're better off by having more augmentation than buying more systems in day one and buy premium on equipment. If your labor market is constrained and you don't have the resources, then maybe it's better to do it the other way. In terms of augmentation cost is significantly less than initial build because you have your substation built out, you have your control system built out, you have your infrastructure built out. So you're just typically you just show up with a new container, install it on maybe a pre-existing foundation or a new foundation that you build, and you tap it into the AC or the DC, which is quite fast process. So augmentation cost, we see in that being almost a quarter of initial capex on augmentation basis. That's not entire cost. I'm just saying on a basis standpoint.
Yeah, understood. The next question will be: how do we evaluate the best projects? Based on capex value, kilowatt hour, or based on LCOS of the life cycle?
Yeah, we prefer to use the LCOS measure, of course, because that you have to include all the costs, not just capex, opex included, but also you have to see how much of the revenues you're stacking and how much that adds up to your as revenue streams to justify a project. Yeah.
Yeah. So in the formula of LCOS, I think you've mentioned about fixed O&M costs. So how about a variable O&M cost? And what is ITC is mentioned in that formula?
Yeah, ITC is the inflation tax credit. It's an IRA. Is it inflation tax? No, it's a tax credit, incentive tax credit. Incentive tax credit, sorry. IRA is the Inflation Reduction Act. So it's basically a government repayment. The US government or the IRS repays battery projects for being green. Your other question is, do we have variable cost? Most of the cost is fixed. As I said, there's a lot of augmentations pre-planned, you know it, and the inspection rate and inspection period is well defined. And most of the warranties with the equipment comes with the corrective maintenance being included. So that's why we see very little, barely anything when it came to variable cost with OpEx.
Thank you. Thanks for your patience.
No problem. Any other questions? I just want to see if there are other. There's two folks in the back that haven't asked questions. We'll get back to it.
Just referring to the Nova BS, what would be the charging time and discharging time? I mean, considering full load available for charging and full demand available to discharge.
So for charging, let me start with discharging. Discharging, this is a 4-hour system. So 4 hours to discharge.
3 gigawatt.
Yes. Yeah. So 4 hours. So if you do the math, it's actually 700 and some change megawatt over 4 hours. That's how you get your 3 gigawatt hours. So it's you multiply your power by the time you get the 3 gigawatt hours.
Yeah.
So you divide 3 by 4, that you get your power. Your charge time is slightly more to account for the losses and the efficiency. So your charging time is about 4.6 hours.
To get 99%.
To get 99%. Yeah.
Okay, that's great.
Yeah.
All right. Thanks.
No problem. Question on the corner, just given the mic in that aisle. Yeah.
Just a quick question on the levelized cost of storage you have mentioned. I always feel that it's a bit misleading when we use levelized cost of storage because it doesn't actually look at the entire picture of the storage with the source of energy, for example, is being charged with a grid or solar, whatever it is. So it might be a bit misleading to kind of look at the economics of the project, for example. I think it's a good tool to compare between different technologies, I agree, but it doesn't really give the whole kind of picture. So I just want to see your opinion on that when you start, for example, evaluating projects, economics, visibility. That's maybe part of the question. The second question, and it's quite related to our area, in Oman, it has been quite difficult to try to convince integrating BSS, especially with kind of a low tariff coming in the area, and it's always it takes a lot of effort to try to show the economics. The economics generally it's not that appealing, and you need to kind of look at some other elements to try to convince your management, whoever it is. But the question is specifically on off-grid systems, where, for example, typically they're using diesel generators. And there is a bit of a trend now going on in Oman, in the region, to try to look at BSS with solar, with possibly also diesel generator as part of it. But that hybrid solution, it's still let's say it's not very vast used, but I've been looking at different economics for different percentages of this integration. But like, from your experience, what is the best way to really look at that integration? From what point of view? Is only economics will be the way to look at it? Is there any other elements we can also look at as well? Yeah.
Sure. So start the first question, which is, theoretically you're asking, are you charging fuel cost for your battery system? Because you're charging it from the grid, you're buying energy. Is that being accounted for in your levelized cost of storage? It is. So basically we treat, and there are different tariffs. I don't know exactly about Oman, but let's call it in the US, they have different tariffs for charging costs for batteries than the regular load. It's a little bit more forgiving in terms of a rate, because you're adding value, as I said, but also it's market driven. So most of the time we like to do is charge at a very low hours or negative pricing hours, because we want to minimize our fuel cost, which is the electricity. That's what fuels the batteries. So it is accounted for in our analysis, and we do consider that as a metric for IRR evaluation. Your second question is regarding microgrids and how we're looking at microgrids. Battery storage is the most critical component of a microgrid, in my opinion. Without it, you can't really have a reliable microgrid at that point, unless it's very high CO2 footprint microgrid. There are a lot of examples globally and in the US about islands going fully, or even just counties or cities, or not cities, counties and small communities going fully off-grid. Personally been involved in a project in Washington State where we did go fully off-grid for a small community of a couple thousand people. On a bigger scale, Hawaii is pretty much a microgrid at this point, a renewable microgrid with so much renewable and storage implementation. So there are definitely instances and a lot of cases where microgrids have shown to be effective. Your question is, or at least in my mind, how you evaluate that is, you can have the goals, and I've been hearing the goals globally, not just in Oman, about net zero, and we want to hit X renewable penetration. Really what we need to think about is, what is our carbon footprint in that energy mix, right? Like, yes, you can have a microgrid without batteries, but you're going to have a lot of your renewable energy generation go to waste and not being utilized, versus you can add the battery as a byproduct, and that can help you lower the carbon footprint of your grid. So if you do that analysis with the carbon footprint in mind, you come to a conclusion where batteries are a very critical component of that. In terms of justifying, that's really policy driven. Are there going to be, and even in the US talked about, is there going to be a CO2 market where you get charged for CO2 footprint? We've seen that in the PJM market, where it's something called Regio. I don't want to get into that in a lot of detail, but it's where you're getting actually penalized for your CO2 footprint, and that's impacting our pricing. That's impacting our approach of the generation mix in the PJM market, where a lot more renewables, a lot more storage are being justified now, because you're going to be charged for your CO2 footprints. Oregon is a great example as a CO2 footprint market. So there's different. Yeah, we start looking at it from a holistic view. You start seeing the value of the energy storage product. There are a question in here. Can we pass the mic? Yeah. Mm-hmm.
So that is mean, يعني, is very obvious that there are some shortcomings from the lithium lithium. That's why it will be replaced by sodium ion. So just we wanted to know what are the shortcomings from the lithium ion compared to the sodium ion, and now is maybe one of the topic that Mohammed has mentioned regarding about the levelized cost of energies and the cost. Whether expecting any reduction in cost, and maybe one of the challenges is the footprint. Whether also is that is we can go for sodium ion, that is the footprint going to be reduced. So we want to know what are the advantages.
Yeah, I'll try to be high level because we're running out of time and lunch is served in a minute here. So sodium ion, the reason it's being introduced, or one big reason it's being introduced, is cost. Because lithium, a year and a half ago, was very expensive, given the lithium mining challenges and processing challenges. Sodium is much easier to manage. But from a performance standpoint, we don't have a lot of data on sodium. I've seen some data from some suppliers that only a year, 2 year old, so it's not a lot of track record on that technology. It shows that it has a lower energy density, okay, lower RTE efficiency, but the cost is significantly less. So, and then you get into different industries that are competing for the same batteries. So if you look at EVs need lithium. If that's a form of LFP or NMC, they need that lithium. So as the EV market scales up and higher EV penetration, we're going to find ourselves in the utility world, we're going to find ourselves without lithium batteries because those cars are much more valuable in terms of revenue streams for the battery manufacturers. That they make higher margins on an EV than they make on a utility scale project. So you're going to find that we're pretty much kind of forced into a corner where we anticipate to find ourselves in a world where battery suppliers are not going to give us lithium, they're going to have to give us something else. So it's kind of getting ahead of the curve and try to kind of really figure out other technologies, have some data, have some information that will help us implement them in the future, if that addresses the question. Cool. Okay, we'll catch up after this. I know we're going to break for lunch now. It's 1 p.m. And thanks, everyone. It was a great discussion, a lot of great questions. I appreciate it. Thank you.